It's weird, eh?
Oh, that one? It's the hair that gets me.
Yeah. Which the Lego thing? Yeah,
Yeah.
it's the hair and the smirk. That's what I get it for my sister.
Custom Lego. Done.
No, what? I have it. I can show you. I can hand it to you. I have it in my
But
own.
it's not like a custom like you have it.
No, it's just Lego.
Yeah,
Okay. I
okay.
should like sue them for like stealing my image.
Wait, you know Karen?
I know who?
Karen?
Who?
She's in your. It's literally in your picture. It says these students on the
Yes.
photo.
See how many students I have?
You don't even know their
Why do you
names.
think I call you sir and miss?
Wow.
We're talking about this because you get to call all of us professor. You have a word that you can use to call us with like shows us respect. I wish there was a word in your like in the Czech Republic. There's a word that I could call you that's like respectful. Like you would say hello professor. I would respond like
Hello,
good
student.
morning.
Hello, student.
Good morning colleague. Colleague is what you'd be called.
I
But
wish.
we don't have that equivalent word. So that's the best I can do is sir and miss.
I appreciate the effort.
You even tagged them.
They probably
No,
tagged
they took my
themselves.
phone.
Yeah.
Right? I wouldn't have tagged. I don't tag. That's the new thing 4chan is trying to make a white supremacist thing.
What are they doing?
Hashtag.
Oh, that's right. I heard about
So let's see if
Let's
they
not-
pull
let's
that
not
one
mention
off.
that.
That would be amazing. Okay, guys, let's do more derivatives. I'm sure you're getting sick of these. But we have to discuss one more thing. Inverses. Okay, so here's our motivating question. How can we compute the derivative of f inverse given f? Alright? Without calculating f inverse, which may be hard or impossible. Alright. Alright, so remember we know how to work with inverse functions. That's where you take the function's graph and you just swap all of the points to get something else. But something else may not be a function in the end. So, I want to extend our rule set for taking derivatives to inverses. So, first we have to sort of have a discussion about, does this even make any sense? So let's just consider an arbitrary line. So consider an arbitrary line. Y equals mx plus b. We're going to call this f of x. So we can invert this line. It's a fairly simple thing. Let's find the inverse. So if we have this, you get that x is equal to y minus b over m, which means that we have f inverse of x is x over m minus b over m. That make sense? Cool. Okay, so we have a line, and then the inverse of the line. So how do the slopes relate here? What's the slope of this line? M. What's the slope of this line? 1 over m. So we found this relationship between a line and its inverse. So what does that mean generally? Well, suppose I give you a curve like this, and we know that this is the point AB, and we have a tangent line that runs through here that's equal to y equals mx plus b. If I look at the inverse of this function, we should have the line BA. There's going to be a symmetry through here. But the point is we're going to get another tangent line here. And the tangent line is going to have slope what? Well, if this tangent line has slope m, this tangent line is given by 1 over m x plus b over m. So does it make sense? Like, okay, so we have a function. We can do all the geometric stuff to determine its tangent line here. Now I want to use the fact that we have a function with a tangent to argue that if we took the inverse of this, there should also be an inverse tangent. Does that make any sense? Like if you just flip this whole picture, you're going to carry the line with it. And it turns out the relationships between the lines Or is the first slope will be m, and the second slope will be 1 over n. We have this sort of relationship between the two functions. Now this is the geometric explanation. It's actually much easier to understand how we get an inverse function by using chain rule. So consider this. So we want now, that's just a geometric argument that the derivative on the inverse function should exist. Tells us nothing about how we would calculate it. Consider this. Is this true?
Yeah.
Why?
It's
It's the definition of
yeah,
inverse.
it's,
Yeah. By definition. Yeah? Okay, so what happens if I take, and I'm going to write this now. When I write this, I'm basically saying, look, I'm going to take the derivative of both sides of this equation. So what happens if I take the derivative of the right-hand side with respect to x? You get 1, so let's just keep, well, maybe I'll just do this. So we're going to get dx of f inverse of x is equal to 1. So I taught you chain rule yesterday, so how can we expand this guy? What's the rule?
first the derivative of the outside
Yeah, derivative of the outside.
times the inside. Oh,
Huh?
no.
No, composed
Compose
with
the
what was
inside.
in the inside,
And then derive the inside.
multiplied by the derivative of f of x. And this is all equal to 1. What do you see here that we've actually found, like that? What have we discovered? I'm trying to find a rule for taking derivatives of inverse functions.
It's-
Okay, so like look at this equation. What stuff do we want and what stuff do we have? Okay, we want this quantity, right? So clearly we don't have it. Do we have f?
Oh, we gotta divide by 1 over. So
No, hold on. Let's walk through this. I'm going to give you f,
Okay.
a function. So can you give me the derivative of that function if I give it to you? Yes. Can you find the inverse of that function at least at a single point? Yeah. So we have this and we have this. That's 1. So actually, what we have discovered is that f inverse, the derivative of this, is equal to 1 over the derivative of f itself, composed with f inverse of x, multiplied by, oh no, that's it. That's it. So do you see now that we have a rule for finding the derivative of the inverse of a function based upon the function itself and the inversion itself. So we can flesh this out more. I'm just going to write this down as a theorem because it's important. Does it have a name? Yeah, derivative of inverses. So what do we got? We got that, and I'll write it in a different way maybe. So I'll write it like this. F inverse of x prime is equal to 1 over f prime f inverse of x. Okay, so it's normally the case that these inverses are like impossible to find. Right, so very rarely are you actually going to be able to do this. So we'll only typically ask you to find the derivative at an actual specific point, as in this example. So let's look at this. So let's just look at the parabola, and I want to find, whoops, maybe I should call this f of x, and I want to find d, the derivative of the inverse. Whoops. At x equals 2. Okay, so try that. I'll give you the answer in a second. Just apply the rule. I want to see if you're able to apply those rules. Okay. Anyone get anything? Probably need more time than that, but at least you thought about it. So what do we have here? Well, first notice that f of, did I put 2? That's going to put roots. Maybe I don't want roots. I lied. I want this at x is equal to 4. That makes more sense. I'll get rid of it. So notice first that f of 2 is 4, which means that f of inverse of 4 is 2. Right? So I now have that value. What do I need now? Well, I'm just going to apply the rule. So the derivative of this is going to be equal to 1 over the derivative of f, which is what? With respect to x? 2x. And then I'm going to compose it with f inverse of 4, which is 2. So don't get confused now. This is still function composition. This is not multiplication. I'm going to take this 2, I'm going to put it in for x. Right? It just so happens in this case it goes to a quarter. Right? But it's not because of multiplication, it's because of function composition. Okay, so does this make sense? Right, I'm saying that if you look at the parabola, so here's the parabola, and then you should have some inverse function like this. What is this saying? It's saying at 2, 4, you should have a slope. Well, what's the slope of this guy at 2?
8.
8. What's the
Oh,
derivative
sorry,
of
4,
this?
4,
4, okay. So at, this guy has slope 4 at that point, and they're saying that the derivative on the inverse function, which is the square root function in this case, should have derivative a quarter. Does that make sense? Yeah, well, it's still positive, but it's very weak, right? So this does seem to make sense geometrically. You should plot them using Desmos. All right, so like basically that's the whole thing. If you can just remember that equation, you're gold. And we'll ask you like take the find the derivative of an inverse, and you just have to do that. If you forget how to do that, just remember how we derived it. Right? You just take f of f inverse of x is equal to x, and you take the derivative, and the equation will pop out. Let's try. Okay, so again, a million examples today. F of x is equal to x cubed minus 2. I want you to find d f inverse dx of 6. Okay, so help me do this. So what do I need? I need to know a few things. I need to know the derivative of f with respect to x. What's that?
3x squared.
Yep, 3x squared. I need to know the value of f inverse of 6. What's that? Remember, you have to guess. Right? There's no strategy here. You just guess. So what number do I have to put into here to produce 6? Is it 0? Plug 0 into that. What do you get? Minus 2. Plug 1. What do you get? Okay, 1 cubed is 1, minus 2 is 1. Put in 2, what do you get? 8 minus 2 is 6. Okay, we didn't have to go too far, so what's this? 2. Right, f inverse of 6 is 2, because f of 2 is 8. 6. 6. Oh my god. This is why I shouldn't have taught today. Okay, so what other pieces do we need? So, okay, if I just want to do this, then all that's required then is to do, just to plop it into the equation. 6 is equal to 1 over f prime at this number. So it's 3x squared at 2, which is 12. Okay, and I want you to plot this with Desmos, just to confirm it. Okay, you try one. Exercise. I'm going to do a lap, so I can have a drink of coffee. Here's f of x. I want you to find find the derivative of the inverse at 5. 1 lap I will give. We should go to Drake for his answer. Don't mean no disrespect, but it's 2. Some more Raptors to do it over here. I tried to find something, but everything's gone. Stop. Check. I'll take it in front. Second line shift. You'll sit up front. Anyone have an answer? Yes.
I got 2 answers? Because I had.
Well, you're wrong. You can't have
You're
2
wrong.
answers, right? I've said that a million times. Right? If it's 2 answers, then you screwed up. There can't. How can there be 2 tangents at the same point?
Because I square rooted 2 and there's a plus and minus.
Okay, you screwed something up. Right? There shouldn't. You don't need a square root. Why do you have a square root? Okay, so what are the pieces you need to solve this? Right? You need df dx. What's that?
4x.
4x. You also need the precise value for this. What is it? Square root of 2.
That's
Yeah,
what I
that's
got.
what I got.
Oh, did I screw up?
It's 210.
Okay. My apologies. Right? All right, so this will still work. Like square root of 2 is fine. I think we just have to sort of like specify which end of the act. Okay, so we'll just check it out. Okay. Shoot. Yeah, you're right. PhDs can make mistakes. I'm a professional at mistake making. How can I fix this? Okay, let's just do it like this.
X cubed.
Boom.
What?
I'll just take that 2 out. We're good to go.
Yeah.
Right? Because now this will be 2, yeah? All right, so okay, again, all we need is so the derivative of the inverse at 5 is going to be 1 over 4x composite 2, which is going to be 1 over, what, 8? What 8? Huh? Oh, God. You know what? Oh, all right. Okay, we'll do it properly. I'm just lazy. 2x squared plus 1. Okay, breaks here, class. We gotta like be on our best behavior. Okay. So let's just give it a try then. Okay, so we get d f inverse of 5 dx is 1 over 4x composite 2, which should be 1 over 4 root 2. Well, you are right. Technically, this has 2 answers. So does that make sense? Oh, yeah, I guess, right? Because, so this is a parabola. I guess we're finding that guy and that guy. Like, there should be 2 slopes here, right? So I could have fixed the problem just by specifying that we're only going to take the positive x. That would have got rid of the bottom branch. So good call. Like, my mistake actually, well, it makes sense why we should get 2 in this case. Okay, I'll give you another one. Okay, I just want you to think about this one. What is the, what's the derivative of ln x? Think about that for a bit. So what is ln x the inverse of? E to the x, so that's a good starting point. I want you to use the rules I gave you to find what this, does anyone know from memory?
1 over
1 over x. Why? right? Not because your math teacher decided, but because it's consequent to some rules. So try to figure out why it's 1 over x. What time is the game? Is it 8? 9?
Thanks.
I don't know if I can make it to 9.
Anybody got a
Okay, anyone have any ideas of how we're going to do this? Think like a mathematician. Or not. Okay, we know that ln of x and e of x are inverse functions, right? So basically what I'm asking you here, like suppose I say f of inverse in this case of x is ln x. Right? In this case, basically what I'm asking you for is this, right? Correct? Right? This is the same question. Okay, so now I'm just going to use the rule that we developed. That's going to be 1 over. Now, if this is our inverse function, what is f? E to the x. Perfect. Okay, so down here we're going to have the derivative of e to the x, which is what? E to the x. We're going to compose that with what? This. And what does that equal? This is going to be 1 over e to the ln x, which is what? Now you know why it's 1 over x. Yeah, it's not so because of magic, it's so because of math. Okay, just keep in mind here that this is a rule that's only good for x greater than or equal to 0, because ln x doesn't have negative values in its domain. Right? So usually when you derive, you have to specify that those values are positive. All right, so more generally, how do you take the derivative of this? What is the derivative with respect to x of ln of a function? You don't need a new rule for this. I've given you a sufficient number of rules, so tell me what it is. What did you learn yesterday? Chain rule. What did we learn that the chain rule strategy was? Work from the outside in. Okay, so I cover this, and I say, what's the derivative of ln? 1 over the thing. Okay. Then what else comes out from chain rule? The derivative of that. Okay. Don't memorize these rules, right? Memorize the 3 or 4 super rules that help you get every other rule, right? Because I don't remember this. I just know that this goes to 1 over x, and then you have to pop out a chain. You always have to pop out chains, right? So this is the more general rule. Okay, here's one for you to try. You may get to redeem yourself from yesterday. What is the derivative of ln of the absolute value of x? One laugh. Or word clear. Now, don't be tempted to just duplicate the strategy we used yesterday. What did we determine yesterday? We found what the derivative of the absolute value of x was. So think of, you know what the derivative of the absolute value of x is. So use it. Don't repeat, don't reinvent stuff that we've already invented.
Is that what you That's what absolute value of x is. Oh. X over absolute value of x. Yes, that's what it was.
I think I got an answer.
What is it?
Is it 1 over x times the absolute value of x?
No.
Alright.
Is it square root x squared over
No.
absolute value x?
That's the 14th
Yeah.
one.
You got an answer?
Yeah, is it x over x, the absolute value of x times the absolute value of x?
That's technically correct, but not simplified enough.
X over the absolute value of x squared.
Is that a thing?
That's getting close. Go all the way, right? Okay, I'm gonna make one lap. And think a little bit harder. Right?
Here, wait. What's the derivative? What's the derivative of
Derivative of absolute value of x. Wasn't that x over absolute value of x?
Yeah.
Was it?
Yeah.
See, that's
Oh,
fine.
I forgot.
So what do you do from here? What do you do from here at this point? If you put the absolute value of x times the absolute value of another one, is this just x over x, or should use 1 over x? I mean, like if you multiply two x's, it's going to be positive anyway. You don't need the absolute value, so you can just take them out at that point, and it becomes x squared. Maybe. Is it 1 over x? Of log absolute value of x. Okay, no, my reasoning was if you multiply two of those together, it's always going to be positive anyways, so you don't need the absolute values. So it could be x over x squared, which equals 1 over x. But I don't know if that's right. I need to ask you.
So x over x squared. Wait, or is it just x?
You guys are going to cheat, and I'm going to go on Wolfram Alpha.
I got like one step. Where do you get the second?
It is 1 over x.
That's it. That's the final
It is 1 over x. That's crazy. Hey, Professor,
Yes, sir.
is it 1 over x?
Uh-huh.
Yeah.
You did redeem yourself. I thought of you when I had this problem, because yesterday you got pissed for not like converting absolute value of x to the thing. And
No,
today that would have been the wrong problem.
That's what I tried first.
I know. Did it work?
No.
I know. Okay, so here we go.
Because
So we
if
know what the
multiply
rule. Okay,
that,
so what we just follow the rules, right? So the derivative of this is equal to 1 over the absolute value of x times the derivative of the absolute value of x with respect to x.
It's the same as 2 squared.
Okay, what did we work this out to yesterday? X over absolute value of x. You get 1 over the absolute value of x multiplied by x over the absolute value of x. So let's continue. So this is x. Now I'm going to put back in the definition of this. This is the square root of x squared. Square root of x squared. This is equal to what? So this is 1 of x over this. So it's x squared squared square root.
X to
So
the
it's
2?
just x.
Well, okay, so maybe we'll do it like this.
It's just
the,
x squared.
it's the square root of x squared squared.
Which is
So
equals
x
x
squared.
I know, I'm just trying to help everyone else get there.
I mean, I'm getting it too now.
Great, so we can move on. He gets it.
I'm not gonna be
You guys seem uncomfortable with these rationals. I don't understand. Like, this is grade 10 was basically like 100% multiplying these. Right, so these just come together, right? So anyways, you get x over x squared, which is 1 over x. Make sense? Make sense? Drake? All right. Makes sense to Drake. At least that's what I assume that facial expression means. Derivatives are fun! Okay. Okay, so now I'm going to ask you a harder problem that is not harder mechanically, but is harder because I'm asking you to take a derivative in a super roundabout manner, which is the way that you have to be used to being asked about questions. So here's your example. / exercise, I guess. Okay, a line solid L with slope M passes through the origin and is tangent to y equals ln of x what is M? Okay, think about this for a bit. What am I asking? Okay, so sort of the best thing to do in these cases is to try and draw a picture. So we have ln of x here, like this. This is ln of x. And I'm going to connect a line from the origin to a point on this graph. And that's going to be called L. Does everyone get that set up? Okay, so read the question. I want you to try to understand what it means. Right? You have a line that goes through the origin. We get to pick what slope it has. The slope that we want to pick is the one which is tangent to this line. Right? So basically, I need to move this point. I need to find where this point has to be in order to get this line to be tangent. Try to get an algebraic expression for that. You're going to have to solve something to get the answer here. I want you to figure out what it is you have to solve. I'll give you a lap. Or we have to decompact. Wait, what's the word I'm looking for? Decompose? I don't know, we have to like flesh this out a little bit more. Decompose it, the parts that you don't understand. Because I will be asking you questions like this. You have to be comfortable. And the tragedy is I know if I were to tell it to you, like, just calculate this f, you'd all be able to do it. It seems that you're all very capable mechanically. But you got to be able to translate questions like this into something that you can do. That's the next hurdle for us. So try to figure out, and you're going to have to solve something, what is it we're solving? Well, let's start with some easier things. What is the equation for this line? Suppose, so this point here is going to be A, say, ln A, right? If we just choose this point A. So what is this line then? If it goes through 0, 0, and A ln A. Well, it's this one. So the line is y minus ln A is equal to its slope, x minus A. Okay, so what's its slope, though? Well, notice it's going through the origin. Right, so the rise over run is easy to calculate. It's this rise over this run. So what's the rise? That's the run. This is A. So what's the rise? Ln A. Right, so this is actually rise over run, x minus A. Okay. So we know that any line that goes through this origin and through this and through a point on the ln x has to have slope equal to ln A over A. We know that the derivative of ln x is 1 over x. Right, so if at x equals A, we have tangent slope what? 1 over A. Okay? So what do we need to find? We need to find where is 1 over A equal to ln A over A, right? That's the A we're looking for, the A that satisfies this condition. All right, so solve this. This is the algebra of that question. Basically what it boils down to. Okay, so can we solve this? What do we get from this? Rearrange some things. Well, what cancels, quite obviously? Something cancels. What is it? Yes, sir. A's cancel. What happens if you multiply by A? This goes to 1. This goes to ln A. Okay, so we get 1 is equal to ln A, which means A is what? Ln of 0 is undefined. E, ln of E. Because I need to take the inverse of both of these things. Ba, ba, ba. Okay, so this one wasn't hard mechanically. This one was hard because you had to like understand what the question was asking, right? So you need to understand what the question was asking. You need to be able to do derivatives, right? So it's both. Both. Don't over focus on doing mechanics. You guys can do it. I'm very confident. I'm less confident in the ability to translate the question statements into things that you can actually go about and solve, right? Because codifying the question into a statement of algebra is that's basically what math is. Right? Math isn't doing arithmetic. That's accounting. And math is this conversion. Right? So please practice both. Because for one, doing this, you're exercising your mechanics as a secondary factor. Right? You're always having to do derivatives to solve questions.
I sort of understand. I need to look over it.
Yeah.
Oh, because if you multiply both sides by
All right, so the next thing we're going to want to do is figure out a rule for taking the derivative of log base b of x. Think of how we could do that while I wipe down these boards. I'm going to wipe down both, actually. So see if you can get a rule for that by using rules that you've been given. You can do it totally algebraically. What's a good first step? Well, did I teach you how to take derivatives of logs? No, what have I taught you to take derivatives of?
The inverse.
Huh?
Well, we can find the derivative of the inverse.
I taught you, what did I? I haven't taught you logs, but I've taught you what? Ln. And we know that there's a relationship between log and ln. That's a good place to start. Right? You want to change the thing that you don't know how to take derivatives of into something you do know how to take derivatives of. So that's your hint.
No, okay, so
Okay, what's another way that we can write this? Using lns.
Ln x over ln b.
Exactly. This is ln x over ln b. Does everyone remember that? You have to remember this. Log of x base b is equal to ln x over ln b. This is important. This is how we're going to take derivatives of logs, because I didn't give you a rule for this. I gave you a rule for this. Okay? So how do I go from here now? What's the derivative? We do? Where's the quotient? What's this? Ln b. What is it?
ln b.
Is it an equation? It's a number. This is a number. So if I said this was like ln x over 2, you wouldn't have said quotient rule. This is a number. Ln b is a number, like 7. I don't know what it really is, but it's a number. You don't treat it as, you don't have to take a derivative of it. Like again, if I said ln x over 2, you wouldn't think quotient rule. Do you understand that this is a constant multiplier? 2 is a number, and so is ln b. Right? Don't treat ln b as special. It's just a number with some special wrapping around it. Right? So, okay, so what rule do we need now, then, if not quotient rule? Okay, how about if I write it like this, then? We have d dx of 1 over ln b, which is just a number, times ln x. Can you do it now? What happens if I just take this out entirely? Can you do it? I just taught this like a minute ago. What is the derivative of ln x? 1 over x. If I multiply by a constant, it doesn't really change anything. Right? So this is going to be 1 over x. Oh. This is 1 over x ln b.
Isn't the derivative of ln b just 0? Because it's a constant.
We didn't take the derivative of. Okay, so I'll do the quotient rule on this. Okay? Ln x over ln b. Let's do the quotient rule. Well, it's the derivative of the top times the bottom minus the derivative of the top. Derivative of the top times the bottom minus
Derivative of the
the
bottom.
derivative of the top.
No, bottom.
Bottom. Jesus, Murphy. Ln b prime over ln b squared. Okay? Okay, so this is what? 1 over x ln b. What's the derivative of ln b?
0.
It's not 1 over b. That was on your exam, wasn't it? Or your practice. This is just a number. A derivative of a number is 0. So you get minus ln x times 0 over ln b squared. And then that will cancel with this. See, but it's a disaster to not realize that you don't need quotient rule. It's like, it took me this versus that. This is a huge waste of time to do it like that. Although it will work. All these rules will work if applied faithfully. Okay, more rules. More rules. And don't forget, you can use this with chain rule. What happens if I ask you to take the derivative of a to the power of x? Do we have any rules for that? No. Right? It's certainly not x a to the x minus 1. Right? That's a different rule. How can we then discover a rule for this? Does anyone have any ideas?
We can use log.
Yeah, we use log, right? So whenever you have the thing that you're interested in the exponent, what we're interested in is bringing it back down. Okay, so I'm going to show you a new technique here. Okay, so I want to figure out what this is. I'm going to use a new technique called implicit. Wait, isn't that what we did yesterday? I don't think this has a name. I'm just going to use a new technique. Okay, so I want to take the derivative of this. So I'm just going to say y is equal to ax, find dy dx, right? That's what we're trying to look for. So notice what I can do here. I can say, if y is equal to a of x, a to the power of x, this means that ln y is equal to x ln a. Does everyone understand this? I just took the ln of both sides of this equation, and I just go ahead and I bring the exponent down, just so I don't have to write it twice. Okay, but this means, if I take the derivative of both sides here with respect to x, I'm going to get 1 over y, what? Y prime, because of chain rule, is equal to, what's the derivative of the right-hand side? Ln a. Right? Because the derivative of x goes to 1, and ln a is just a number, so don't treat it as anything special. Okay, this means that y prime is y ln a, but we know that y is equal to a to the power of x, so actually what we have is a to the power of x ln a. So you see, this is actually equal to x, a to the power of x ln a. So I don't actually care about memorizing this, although if you do end up remembering this, it's going to save you a lot of time. In my opinion, it's more important to understand how this technique got it out. Right? So you can always take derivatives implicitly by bringing stuff down out of the exponent to the gram. Okay, do an exercise. This should not take you one lap, but let's see. What is d dx of a to the f of x now. That's the first one. And what is Murphy. Yes. dpx 3 sine x, and then c, what is dx 2 of x? Start with this one, it's the easiest. I'll make one lap.
Yeah, but that seems too easy. Because then it would just be ways of
Okay. So this guy should be a of f of x, f prime of x. Right, because this is just the derivative. Oh, what am I doing? Oh my god, totally wrong. A of f of x ln a multiplied by f prime of x. I'm just utilizing the rule that we just developed, but don't forget about chain rule. That comes out of here. Alright, so the same thing for this guy. You're going to get 3 to the sine x ln 3, but then I have to multiply by the derivative of sine, which is cos. This is the easiest one down here. This is just going to be 2x ln 2. Okay. So this is kind of a neat trick. So I'm going to show you a neat little strategy here. when you're given a derivative that looks kind of hard. So this is a strategy called logarithmic differentiation, and it works like this. So here's a function, x squared plus 1 root x plus 3 over x minus 1. Now, you could do it the way that I've shown you by doing a quotient rule and a product rule and then a bunch of chain rules. It's going to get messy. It's going to get messy. There's a new strategy I'm going to teach you here, and that is, even though there is nothing in the exponent, I'm going to show you it's still actually worthwhile to use a logarithm to solve this problem. Because this means what? If I take the ln of both sides, ln of y is equal to what? So what are the rules we have for lns? So what's the ln of a product of things? Yeah, ln of a times b is ln a plus ln b. Okay, so that means if you divide by something, you're subtracting it. So we at least have ln of this plus ln of this minus ln of this, correct? Okay, but this one has a square root on it, right? So we also have the rule that ln of a to the power of b is b ln a. So this is actually ln of x plus 3 to the half. So let me do this. Right, so another way of looking at that is like that. So hopefully you'll understand what I write here. We're going to get ln of x squared plus 1 plus 1 half ln of x plus 3 minus ln of x minus 1. Okay? This means that I take the derivatives of both sides with respect to x. What am I going to get? 1 over y prime is equal to 1 over x squared plus 1 times the chain rule. So what comes now? Huh? 2x. Right? So it's 1 over the thing I don't care about times the derivative of the thing inside, which is 2x. Then you're going to get 1 half 1 over x plus 3 times the derivative, which is 1 minus 1 over x minus 1 times the derivative. Be careful when with signs. You may get tempted, like ln of minus x is going to be minus 1 over x because of the chain rule. Okay, but this means that y prime is equal to 2xy over x squared plus 1 plus 1 half y over x plus 3 minus y over x minus 1. Now, I know you're going to complain about this. You're going to say, look, there's a y. Yeah, there is. But what's more simple? Do you think this is more simple? I say, look, y prime is equal to this, where y is equal to this. Right? Or should I go ahead and put this equation in for each of these y's? To me, that doesn't make it more simple. That makes it more complicated. Right? This is totally fine. Y prime is this, and y is that. It's a perfectly fine representation of the derivative. Now, if you needed to, if I said something on a midterm, I insist that this is going to be only an x, okay, then you have to bring it in. But this is suitable. You could read off derivatives from this if you needed to. All right, so that's a good technique, right? So, and I'm never going to say something on your midterm like, use the logarithmic differentiation technique on this problem, right? I will instead give you a problem where if you don't use that technique, it's hopeless. That's more mean, right? So you got to be aware of these techniques. I'm teaching you these things for a reason. Here's a tool that's going to be useful when you see things of that form. So I just sort of like put that into your toolkit now as something that you can try if you're getting a derivative that like looks like it's exploding. So this can maybe simplify it a bit. Okay, so what I'm going to do now is I'm going to write you a few more exercises on the board. So this is the first half of the class is over, so why don't you guys take 10, and we'll recommence in 10 minutes. Yeah, I'll give you a few more questions. You can talk and stop.
No, she was like this is just one.
Same rules for A.
Yeah.
But for B, he's just making sure to use the chain rule afterwards. That's the only difference. Oh, the one who just did here? So, what he did is that he, first of all, So no, so look, if you took the log of all of this like that, it would be, first of all, so it would look like this. It would be like log A, B over C. You know that if it's log A over B, it would be log A minus log. So log A minus C, that's log A plus log B minus log of C. Log there, log of C. So that's
I'm just talking to you two.
Same thing. So imagine this is A.
It's not going to stop everything.